Hi, this is Sally's Book Talk, bringing you the best books from around the world every day. Today's featured book is The Case for Mars, subtitled A Plan to Settle the Red Planet. On December the 11th, 2017, U.S. President Trump signed a space policy directive at the White House announcing new space exploration goals. The plan aimed to return astronauts to the Moon and eventually reach Mars. This directive set NASA's course for years to come and reaffirmed Mars as the ultimate goal. This vision excited both the aerospace industry and space enthusiasts worldwide. The book, The Case for Mars, we're discussing today is directly connected to this news. It provides a technical blueprint for human settlement on Mars. Author Robert Zubrin is a renowned aerospace engineer and founder of the Mars Society. In 1990, he proposed the Mars Direct mission architecture. This $40.50 billion plan was not only significantly cheaper than NASA's $450 billion proposal, but also more feasible and reliable. As Carl Sagan noted, Zubrin has almost single-handedly changed our thinking about this issue. The Case for Mars. The book details Zubrin's Mars Direct plan and outlines the process for establishing semi-permanent bases and eventual colonization. First, we'll explore this book through 4 key sections. First, why should humans go to Mars? Third, what challenges must we overcome to reach Mars? Second, how will the Mars Direct plan get us there? Fourth, how can we achieve permanent settlement? Now, let's open this book and embark on humanity's greatest journey to Mars. First, why should humans go to Mars? First reason, Earth is becoming overcrowded. Konstantin Tsiolkovsky, father of astronautics, said, "Earth is humanity's cradle, but we can't stay in the cradle forever." This metaphor explains humanity's relationship with Earth and our cosmic destiny. Just as children must grow up and face the world, humanity must eventually leave its planetary cradle. As issues like population explosion, global warming, and resource depletion intensify, humanity's cosmic expansion becomes imperative. In just 2 centuries since the Industrial Revolution, we're already facing resource exhaustion and climate crises. Scientists estimate 16 critical industrial minerals will be depleted within 50 years. Within 200 years, resources like oil, iron, aluminum, copper, and tin will be exhausted, like ships stranded without ports. Humanity risks planetary entrapment unless we develop space habitats within 2 centuries. Second reason, Mars serves as humanity's cosmic launch pad. Mars confirmed mineral deposits. Subsurface water and CO2-rich atmosphere offer vital resources for space exploration. More crucially, Mars provides access to the asteroid belt's immense resources. The asteroid belt between Mars and Jupiter contains over 500,000 space rocks. These solar system remnants hold rare metals and elements. As Earth's resources dwindle, these celestial bodies become cosmic gold mines. Mars-based operations become essential for future asteroid mining. Earth launches require 50 times more fuel than Mars-originating missions. From Mars, we could transport asteroid minerals to alleviate Earth's shortages. Third reason, Mars remains our solar system's most viable second home. How habitable is Mars? Compare Venus's 480 degrees C oven-like surface, Saturn's 130°C deep freeze, Jupiter's 9-hour days. Could you commute to work? Mars offers rocky terrain, temperatures from 17 degrees Celsius to 90 C, and 24.6-hour days. Like Earth, Mars has solar radiation protection and seasons, the only other planet where plants could theoretically grow. Martian polar caps store massive, frozen CO2 deposits. Heating these caps could trigger atmospheric CO2 release, initiating planetary warming. By terraforming Mars to prevent water condensation and using orbital mirrors to melt surface ice, we can initiate atmospheric water cycles. Introducing cyanobacteria or primitive plants could generate oxygen, potentially making Mars Earth-like habitable within centuries. You might ask, if Mars is our best option, why haven't we launched yet? This leads us to the challenges addressed in Part 2. The remaining obstacles for Mars colonization. First challenge: the immense interplanetary distance. At closest approach, Earth and Mars are 56 million kilometers apart when aligned on the same solar side. Current technology requires spacecraft to follow orbital mechanics along a 400 million kilometer arc trajectory. This 258-day journey must launch during brief 3-month windows occurring every 26 months. Miss the window? Wait 2 more years. For perspective, Earth-Moon distance is 400,000 kilometers. Mars journey equals 1,000 lunar trips. Apollo's 3-day moon trip would theoretically take 8 years to Mars at same speed. Fortunately, reality differs. Modern propulsion solves this time dilemma. Apollo's lunar approach required speed control. Mars's gravity and atmosphere allow faster trajectories. Spacecraft can utilize Earth's orbital velocity, 30 kilometers, Bren/s for momentum boost. Mars-bound ships align with Earth's solar orbit direction for speed advantage. Fuel-efficient routes take 258 days, high-speed trajectories reduced to 150 days. Second challenge: engineering, massive Mars spacecraft. Mars entry involves heat shields for atmospheric braking, then rocket-powered landings. Mars' thin atmosphere. 1% Earth's density renders parachutes ineffective. After establishing base camps, astronauts require heavy-lift rockets to escape Mars gravity for return. Thus, the spacecraft must carry flight habitats, surface modules, ascent vehicles, engines, fuel, and solar arrays, surpassing the International Space Station in complexity. NASA's 1989 90-day study proposed 710 spacecraft requiring orbital assembly due to launch limitations. This necessitated constructing dedicated orbital assembly stations. Third challenge: astronomical costs. NASA's $450 billion budget request equaled 10% of 2017 federal spending versus actual $19.5 billion NASA funding. Congress rejected the plan, redirecting NASA toward Earth orbital projects. Full redundancy requirements caused exponential cost growth in integrated systems. Orbital infrastructure, workshops, habitats, fuel depots duplicated space station costs. Even per-date versions remained at $120 billion, still politically untenable. Zubrin's Mars Direct approach revolutionized mission architecture. Part 3 details Mars Direct's 3 key innovations. 1. On-site fuel production. 2. Multiple small spacecraft. 3. Permanent colonization focus. Original plans required 96 tons of Earth-launched return fuel, astronomically expensive. Mars Direct uses atmospheric CO2 plus imported hydrogen to synthesize methane oxygen. 6 tons each yields 108 tons fuel. Solutions needed for slow chemical reactions and production risks. Solution: send unmanned, fuel factory first, crewed ship after confirmation. Crewed ship becomes surface base. Unmanned ship handles return. Eliminates fuel transport needs, while ensuring return system reliability. This approach dramatically improves mission success probability. Unmanned ships use slow Hohmann transfers, requiring minimal fuel. Each ship under 100 tons, within 1960s Saturn V launch capacity. Eliminates orbital assembly needs, radically reducing costs. The Mars Direct approach budgets under $50 billion, significantly cheaper and more feasible than NASA's $450 billion plan. Mars Direct isn't just political theater. Zubrin plans 2 crewed missions with 500-plus day surface stays. Astronauts leave behind functional bases, with subsequent ships serving as emergency shelters. Follow-up missions depart during next launch window. If initial return vehicles fail, backup ships arrive within 5 years through 3 launch opportunities. Every 26 months, 2 new ships expand infrastructure until semi-permanent habitats emerge. Colonization finalizes in 3 phases. Phase 1. Build radiation-shielded domes using iron-rich Martian soil or deploy 50-meter crater tents. Extract water, iron, produce plastics from CO2, establish greenhouses and nuclear power stations. Phase 2. Transportation costs drop to $100 kg $320,000 per person for 3.2 tons of supplies. Solar sails could reduce trip costs to $30,000, mirroring 17th century transatlantic migration incentives. Phase 3. Mine asteroid belt. Single 1 kilometer asteroid contains 200 m tons iron plus $100B platinum. Mars exports minerals to Earth while receiving technical support, establishing colonial-era trade dynamics. Martian real estate offers investment potential. $50,000 dome homes with 400 square meters space. Corporate participation. REGI. SpaceX could reshape global geopolitics through Martian development. Having outlined Mars Direct, let's review The Case for Mars. Authored by Mars Society founder Robert Zubrin, this seminal work details Martian exploration, challenges, and solutions. The book addresses 4 key questions. First, why Mars, its Earth-like conditions, make it humanity's best cosmic stepping stone. Second, the challenge of interplanetary travel requiring precise 26-month launch windows. Optimal trajectories occur every 25 months with 3-month launch periods. Third, technical solutions like ISRU, in situ resource utilization for fuel production. Fourth, establishing permanent colonies through phased infrastructure development. Zubrin's vision combines practical engineering with frontier spirit, charting humanity's path beyond Earth. Manned missions require massive equipment. Mars ships need costly orbital assembly. Third, how does Mars Direct achieve our goal? Technical solution: split into outbound. Return ships using Martian CO2 for fuel, each under 100 tons. Deploy return ships first, then crewed missions every 26 months for continuous base expansion. Fourth, settlement requires establishing self-sustaining systems beyond initial landings. Martian economic development will drive social transformation through new industries. As H.G. Wells said, we must embrace the cosmos or perish on our dwindling Earth. This embodies the profound significance of Martian exploration. The case for Mars's summary complete. Find keynotes below the audio. See you tomorrow.